right, welcome back to recursive formulas. This is just going to be the simple stuff today. All right, we're going to assume that my first term of this sequence is 5. So that's me saying A1 equals 5. I could say the next term is 2 more than that. That would imply that the second term is 7. And the next term, the third term, is 2 more than that. And the fourth term is 2 more than the third term. Now, here's the generic way to write that. The fourth term is the third term plus 2. And in general, this will always be true. The fifth term is the fourth term plus 2. The 17th term is the 16th term plus 2. And you're thinking, oh, this is a dumb way to write this. Don't forget the Latin term. The root word for recursive is recursi, meaning terrible way to teach math. Anyway, we could extend this pattern. The 100th term would be the 99th term plus 2. I could also, if I were going to extend this list, I could stop at some point and say, what about the nth term of a sequence? This is what we do. We count up, starting at 1 up to the number, and the big question here is what term comes before the nth term? And I know some of you who've mastered the alphabet are thinking the mth term, which would be an interesting way to write, because you're thinking the letter M comes before the letter N. Right, but that's in an alphabetic sense, not the numerical sense. So there's got to be a different way to write this. Let me see. Let me see if we can discover this pattern. The number 3 comes right before 4. 4 comes right before 5. And notice 16 is 1 less than 17. And 99 is 1 less than 100. So I guess the question is, what is 1 less than n? And you're right if you shouted n minus 1. So here's how you would write this generic pattern. In general, this is just saying to figure out any term, this is any term, you take the one before it and add 2 to it. Some of you may be tempted right away to say, oh, I know what n minus 1 plus 2 is. All right, avoid that temptation because that's not what we're doing. Let's try another example. I could define a sequence recursively like such. I have to tell you what the first term is. I could pick anything, like 7. And then in general, I could say, to make this sequence, we're always going to add 5. So remember, the first term of this sequence is 7. They gave us that. I kind of hinted that the next term would be 12 because I told you we're always adding 5. This is kind of how our mind operates. We see this information and we're like, oh, start at 7, add 5. So here's the algebraic way to say start at 7. That's what this means. And then now to figure out any term, this is the nth term. Take the one before it, which is the n minus first term, and add 5 to it. All right, I hope that sits well. So far, all these examples have been arithmetic recursive formulas. Here's a similar one. I'll just give you the information. Well, let's see what we can discover about it. Now some of you are thinking now, oh, easy. They gave us the first term as 18, and then from there, you subtract 1, get 17, and then subtract 3, get 14. Nope. Here's maybe a slightly different way to think about it. This term right here, that whole thing in red, represents the previous term. Here's another way to think about it. They gave us the first term as 18. So here we're searching for the second term. If I put a 2 in for n here, and here, this thing, if you notice, if you do the math, now we can subtract 1 from 2. So really that statement just says that the second term is the first term minus 3. And we get 15. And now, generically, I can use this recursive definition to calculate the third term by putting a 3 in for n. You still have minus 1, from which we're going to subtract that and get 2 in a minute. So really, this thing generically says to figure out the next term, you take the previous term and subtract 3. This is a more specific example. This says specifically to figure out the third term, you take the second term and subtract 3. The third term is 15 minus 3. The fourth term is 12 minus 3, etc., etc., etc. This is a terrible way to figure out the 100th term. If you ever have this type of definition and they say calculate the 100th term, and you put a 100 in there, you would notice that all this means is that you take the 99th term and subtract 3, which was fairly obvious. We're subtracting 3 each time, minus 3, minus 3, minus 3. So obviously, you would take the 99th term and subtract 3. But sadly, you need the 99th term. And to calculate that, you need the 98th term and the 97th term and so on and so forth. So this is really not a great way to calculate large terms in your sequence. It's just a good way to notice a pattern and describe it very quickly. That's what we're going to try to do this time. This time I'll give you a sequence. It will be arithmetic. We'll see if we can come up with a recursive definition for this formula. First term is 12. That's a given, so we could just restate that. A sub 1 equals 12. Fairly easy. Now we just notice that to get from each term to the next, we're adding 2. So we just say that to get to the nth term, you take the n minus first term and add 2. I know it sounds dumb. That's the way you do it. All right, I'm going to give you a taste for the next episode, which is recursive geometric expressions. Not tough. I'll use a little G sub n here. Don't forget, geometric means you have a starting value and then you're constantly multiplying. We notice here that we're constantly multiplying by 2, I hope. Just have to think about how you write this information. You still state the obvious. The first term of this G sequence is 10. To calculate the next term, you take the previous term, that's this, and multiply it by 2. It's really not a bad practice to throw these guys in parentheses. One more time, if you're trying to figure out the next term of your sequence, you take the previous term and double it. Now some of you are like, why don't you just say that? Why do we have to say all this stuff? Great question. All right, have a great afternoon.